This is What's New in Aerospace. My name's Marty Kelsey. I host a television show for middle school students from here at the museum called STEM in 30. Today, the Smithsonian is holding an Ingenuity Festival here at the museum. We have some incredible stuff going on. We've had hydrogen cars, we've had aerial robots flying around for the first time in the museum's history, and we've had incredible guest speakers. I'm joined by Dr. Nicholas Bohrer, who works on the X-57, an all-electric airplane. Nick, we're going to thank you for joining us today.
Thank you very much, Marty.
Now, I want to remind everybody before we get started that you can submit questions. If you're here in the gallery, you can come over to the microphone and ask questions. And if you're watching online, head over to Facebook Live, go down to the comments section, submit those questions, and we will try to get as many of them answered on the show today as we can. Nick, X-57, an electric airplane, tell us about it.
Absolutely. First off, thank you all for coming here today, and thank you all online for joining us. It's an amazing feeling to be here in this building surrounded by all this iconic aerospace hardware, and to talk about a project I really enjoy working on with a really excellent team, and that is the X-57 Maxwell. As you mentioned, it's all electric. That's actually part of the name. James Clerk Maxwell was a 19th century Scottish physicist who, amongst many other things, discovered some of the fundamental relations between electricity and magnetism. This is one of the reasons why we have electric motors. X-57 has a whole lot of them. You see 14 propellers on this airplane. Each one of those propellers is driven by an electric motor. Now, the X-57 is not the first all-electric airplane, and it's not the first one to use a whole lot of different motors, but it's the first airplane. It's a flight demonstrator actually for a particular technology that we call distributed electric propulsion technology.
So what does that mean, distributed electric propulsion?
So it means that we have a number of different electric motors distributed all along the wing here, and they each have a little bit of different purpose, but all together, when you put this on this airplane, we think that it'll give you up to a 5 times reduction in energy used for this airplane compared to a conventional gasoline-powered airplane.
5 times, that seems like an awful lot.
Yes, certainly. But it doesn't all come from one place. So we're not even actually starting with a brand new airplane. As a flight demonstrator, we try to do things as cheaply but effectively as possible. So we start with an existing aircraft. That aircraft is the Technum P2006T, and you see an image of it here on the screen. It actually carries about 4 people normally. One of them is the pilot. It weighs about 2,700 pounds, and it has 2 100 horsepower gasoline engines.
And so this is just a normal, airplane that somebody really rich could go out and buy.
Not even really rich, but I mean, certainly it's not the cheapest thing on the world that you'll go out and get. But what we are trying to show is basically 3 different improvements over this type of aircraft. The first one and the biggest one comes from changing out those 100 horsepower gasoline motors with electric motors. When we talk about efficiency with motors, we talk about how much of the chemical energy stored in the fuel transfers over to the useful energy that turns the propeller shaft. For a typical electric motor, or a gasoline motor about this size, including the ones in your cars, they're only about 30% efficient. The Maxwell, and that's not just the gasoline motors are poorly designed, that's just thermodynamics. If the gasoline motors on the X-57 are about 92% efficient. So you see right there's about a 3 times benefit that comes to it.
So how powerful are the electric engines compared to the gasoline engines?
They're about the same power, but I think our electric motors, the biggest ones, are about 80 horsepower. You can get up to about 96 peak. The smaller ones are a little bit less. They're about 12 or 14 horsepower. But the real challenge, the reason why people aren't all using electric for that 3x benefit, is in energy. There's a whole lot more energy that is stored in fuel than there are in batteries. If you actually took the battery cells that we use on Maxwell and compare it to the same weight in fuel, you'd actually see about a 60 times difference in energy. This is a really big problem, particularly when you need to be able to lift your airplane up in the air.
So how does wing shape play into all of that?
So that's where we get really our second benefit to get us to that 5x number. What we see here on the screen is actually a comparison of the wing shapes of the Technum that we are modifying and NASA's X-57. And you'll notice that the NASA's X-57 wing is a whole lot smaller. And this is actually an age-old compromise in aircraft design that we're trying to kind of cheat. Normally, when you have a big wing, you can go pretty slowly, but that wing can still generate enough lift to take off and land from pretty short runways. But then when you go fast, you need to have a really small wing in order to basically not have a whole bunch of air resistance and drag. So we try to do both. We actually trick the wing into thinking it's going faster. You see here in the video that we have playing, we have all of these little propellers spinning for takeoff, but then during cruise, when you're going fast enough and there's enough air going over the wing, those propellers fold back, and we only end up flying on the propellers out on the wingtips.
Wow, so how efficient and how powerful are those wingtip propellers?
So that's where we get the majority of our cruise propulsion is out of these wingtip propellers. And this is actually our last major contribution towards that 5X number. So there's a couple of things going on. You see here from some of these images, one of the problems of a lifting wing is it creates what we call a wingtip vortex. So like a little tornado, and you can see the manifestation of it here kind of with this crop duster. One of the things that does is that's another source of drag, it's another source of inefficiency associated with the aircraft. Now the interesting thing is, propellers, as when we think about it, what you like out of propellers and fans is you like all that air coming back at you, and that's the useful thing that the propeller is doing to propel you. But what it's also doing, and you can kind of see that corkscrewing motion, is that air is also moving kind of in the circular and this helical motion. That's another source of inefficiency associated with the propeller. So what's interesting is we know which direction the wingtip vortices go. We know they go from the bottom of the wing up to towards the top. So they're spinning kind of this way if I'm facing you. Well, we put these propellers out at the wingtips, and then we spin them in the opposite direction, and then those two kind of cancel each other out, so it gives us another little bit of a benefit by putting all of that thrust out at the wingtips.
So you guys, even though you're working on experimental planes, it really all comes back to the basics, those 4 forces of flight.
Absolutely. Absolutely. So what we're trying to do is normally when you think of propulsion or propulsion for airplanes, you think of thrust, that's the force that's pushing the airplane forward. We're actually trying to alter other forces of flight, like the lift and the drag of the wing, using what is traditionally propulsion.
Now, have you guys done wind tunnel testing with that?
Well, what we tried to do early on, we knew people have done wind tunnel tests of that wingtip propeller. People know how efficient electric motors are versus gasoline motors. And people have done some tests of propellers in front of wings, but not kind of to this extreme. So the first thing that we tried to do here is we tried to fly a truck. The truck never actually took off, but it did get a little bit lighter, and that was the important part. So this is actually a pretty small wing. It's even slightly smaller than the one that's going to go on X-57. It has 18 even smaller props than what I just showed you here. But what we learned from this test is that we were able to get about twice as much lift out of this wing at the speeds that we want to take off and land, and that's when it's really critical to be running these things. So we actually got as much lift out of this little wing, over 3,000 pounds, to be able to lift our airplanes at that low speed that we want to be able to fly so we can take off and land.
Now, the propellers that you talked about, you know, on old airplanes, they provided that thrust to get the plane in the air, but this is actually helping create the lift as well, right?
That's correct.
How's that work?
Well, so it's really, you know, the way I like to think about it is if you ever stick your arm out of a car window or something and you do the little wavy thing. What you might notice if you do this is that as the car goes faster, you feel more and more forces on your hand. Well, you only need to generally create enough lift on a wing to be able to lift the weight of the airplane. So at some amount of time, you're going fast enough that you can just start putting your hand a little bit lower and lower, because if you stick it way up here, it goes and it blasts back. So what we're doing is at these low speeds, we're blowing all of this air over the wing to basically cheat the wing and to think it's going faster. And that's one of the things. And then I said the other one is that swirl effect from the wing.
Can we look at the engine again?
Sure.
I just want to talk us through the, you know, kind of how that idea came to be to put a whole bunch of these out there and use those for the takeoff.
Sure. So there's been a lot of just like all research is you know, you stand on the shoulders of others that have been trying this. You can do all of this without electric motors. People have looked at putting engines in front of wings and cross shafting and anything else to get that extra. This is a known phenomena The biggest challenge, and where electric kind of ended up being a game changer, is how electric motors scale in terms of, we call it their power to weight ratio, how much power they put out for how heavy they are, and how efficiency is. Most combustion engines, the smaller you make them, the less efficient they get, and then you have bigger problems with the power to weight ratio. That doesn't tend, and there's always caveats, but it doesn't tend to be true with electric motors. So all of a sudden, doing things that you would never think of before, like putting a whole bunch of engines on, we've gone the opposite direction with jets, right? We go fewer and fewer and fewer engines because they get more efficient that way. The physics are just fundamentally different with electric motors. And so that allowed us to go back and revisit some of these powered lift type concepts.
So that leads us to a Facebook question. Why will the final design require those 14 motors?
Well, there's we actually, when looking through the design space of this aircraft, we actually evaluated over 3 million different combinations of different design variables to come up with that final wing. And it's a really delicate balance. One of the hardest parts about getting the number of high lift motors right is actually landing. So propellers generally produce thrust, which you'd like to think is a good thing, and it's great for climbing. When you come into land, you're kind of gliding in. You normally would speed up if you kept adding thrust. So we had to balance just the size of them just right, so we could still have those fans blowing over the wing, providing a little bit of thrust, but more providing the lift that we need, and still be able to descend. So that's why we ended up picking the 12 high lift motors, and we have 2 wingtips, and so it was pretty, we knew where we wanted to put the thrust producing propellers. But we looked at a range of everywhere from about 10 to I think up to 18. And that sweet spot was right around 12, it was about 10, 12, 14.
Wow. If somebody wants to learn more about the X-57 project, where do they go?
So the best place to go right now is the folks at NASA Armstrong have put up a fact sheet that on the X-57 that describes it. But I'd just say honestly, we've been trying to go out and speak with different media outlets. So in your favorite search engine, you can take a look for X-57. But one of the big things that we're doing from the technical standpoint is we go out to a lot of conferences. We're trying to publish a lot of papers on a lot of the principles and the design and the test procedures that we have associated with this. So that's all archived as part of NASA's STI process.
I think that's really interesting how you do all of this research and then share it out so that others can build on that. You know, today's all about ingenuity here at the Smithsonian and invention, and it's building upon what others have done.
Absolutely, and it's there's a delicate balance to be struck, right? I mean, one of the things that actually gives intellectual property value is some degree of exclusivity, but there needs to be some baseline pieces out there. So when we come into these very new areas, like with electric aircraft design, it's good to at least have some stuff for people, to have a foundation for people to build upon that can then do their own tweaks and bring their own inventiveness to it, so that they can come up with the next winner.
So I'm a teacher. What would you tell a middle school student watching this? You know, what advice would you give them?
I think it's the thing that I value the most in people that I work with is actual an intellectual curiosity. So why does it work? And so that doesn't mean, just say you're wrong and I'm going to go find out on my own, but just to really try to build your own model. Why does this work? To really think about it in your head. I think that's been one of the most important things ever that's really helped me out. I'll give a very quick anecdote. When I was about 9 years old, I think it was, I asked for chocolate chip cookies, and my mother handed me a recipe, and she said, you can read, you can cook. Now, she stayed there and she helped me and she walked me through what flour was and what a cup was. But it was a very powerful learning moment because it was like, by the way, I can figure this out. I might need a little bit of help, but now all of a sudden I had a model from which I could work with the next time I wanted cookies.
That's really cool. Nick, thank you so much for talking with us today. This has been really great.